All right, so we're going to start by just going back over and reviewing a few things that we did in the first part of 6.1, and then we'll finish up the second part of 6.1 in a little bit. So we started looking at trig. One of the most important things in this section was learning how to convert between degrees and radians. And I know we didn't have a ton of time to practice a lot of them, so we'll practice a few more. All right. So we started out by looking at the definition of an angle. Okay, so we talked about it having two sides. Depending on how you draw an angle, you can either draw an angle in a polygon, or you can draw an angle all by itself. If you draw it in a polygon, like a triangle, two sides are line segments. But when you put it by itself, they're rays. The angle has two sides, an initial and a terminal. And we learned how to identify them, but then we learned how to draw angles in standard position, which makes them very easy to identify. Okay. So the initial side is the side that you start at, and the terminal side is as you rotate counterclockwise, the side that you would end at. We had different Greek letters that we mentioned. Okay, these are all different variables that we'll use for angles, depending on the problem. I'd say theta is probably the most common one when you're talking about a single angle. When we have to talk about three angles together, like in a triangle, a lot of times we use the first three, alpha, beta, and gamma. Okay, in trig, we always use Greek letters for angles, and we use English letters for sides. That just makes it clear that if I'm asking you for alpha, you know it's an angle. Okay? Some books will do capital and lowercase letters, but then that can be confusing because some capitals and lowercase look the same.
For example, C.
Like the letter C, and then if I even said to you like find B, well, then you wouldn't know which one I mean. Does he mean the capital B or the lowercase b? So we're just going to avoid that. English letters for sides, Greek letters for angles. Okay. Drawing an angle in standard position kind of gives us a way that it would look the same, okay, for everyone who drew it. And it always puts the initial side on the positive x-axis. All right. Then we started talking about the different ways we can measure angles. Degrees is one way. When you get into higher level math classes, it's not the way that's going to be used. So we talked about a different way. What's the other method we talked about besides degrees? Anybody remember the other units? Yeah, we talked about radians. So we looked at different amounts of rotation on a circle. So when we use an angle to measure something, it can be used for a couple different things. Okay. One thing it can be used for is an amount of rotation on a circle. It can also be used to measure an angle inside of a shape. Okay. Little bit different idea, but still kind of using that angular movement to measure something. And we're going to talk more about angular movement today to measure things too. All right, so full rotation was 360. How about a half rotation? How many degrees in a half rotation? 180. Yeah, and then in a quarter rotation, that would be, 90. Yep. When we're looking at rotation on a circle, there are two directions. Counterclockwise is always considered positive, clockwise is negative. If you have an angle that's larger than 360, that's fine. It just means that you've gone around the circle more than once. Generally, though, we don't like to work with angles that are larger than 360 or smaller than 0. The reason being is because if it's too big of a number, it's hard to visualize. Like if I said to you, I want you to visualize a 1250 degree angle. Well, it's gone around so many times, it's kind of hard to think about. So to find something that's equivalent in trig, but smaller, we can add or subtract 360 as many times as we want. So if you had an angle like 1250, and we had to do some trig with it, it's going to be easier to subtract 360 and work with a 170-degree angle. That's something most people could visualize. Okay, it's a little bit less than a straight angle. Right? Straight angle would be 180, so it's just a little bit less. All right, so then we did some examples where we took angles and we found an angle that was coterminal and positive, coterminal and negative. What would be the first angle that you get here that's coterminal and positive? Yeah.
Positive 390.
Yeah, positive 390. And what's the first angle that you would come across that's coterminal with 30 and negative? Yeah.
Negative 330.
Negative 330. Yep. So we did a few different angles. And then I think we talked about acute angles, right angles. Yep, different definitions. So acute angles between 0 and 90. Right angle, how much is that?
90.
Exactly 90. An obtuse angle?
Over 90. Over 90 and less than 180.
Yep. So greater than 90, less than 180. And then what do you call the pair of angles if they add up to be 90? So this applies to a pair of angles. Yep. Complementary. Yep. And what do you call a pair of positive angles that add up to 180? Yep, supplementary. Okay, and there were some questions I think on the test where you just had to find a complement and a supplement. What did we say about negative angles? Like if I asked you to find the complement or the supplement of a negative angle? Yeah,
Doesn't exist.
doesn't exist. Negative angles do not have complements or supplements. Okay, so we practiced some of those. And then the last thing we did was talk about radians. I'm going to go a little slower through this. So radians was another way to measure an angle. We talked about what a radian looks like visually. So if you draw an angle in a circle, and that arc in red and the radius are the same, then you've drawn a picture of one radian. That's going to be important for something we talk about today. Right? So if you make this angle, or if you make this arc exactly the same size as the radius, then you've just drawn a picture of one radian. Okay? So keep that in mind for what we're going to do that's going to be new. Okay. All right, now the last thing was converting between degrees and radians. Does anybody remember the 2 steps involved to convert from a degree to a radian? Yep.
Divide by 180
Mhm.
and then multiply by pi.
Yeah. So the order you do those 2 steps in, it doesn't matter, but you just have to multiply by the pi and divide by the 180. Yep. And then how about the 2 steps to go the other way? Change from a radian to a degree. Yeah, right?
Divide by 180, divide by pi.
Yeah, so we've got the multiply by 180 and divide by pi. Now there's a pretty easy way to remember it because it can be confusing. They're very similar, but just a little bit different. When I say degrees, okay, I always want you to think of the number 180. Okay, so in your mind, just kind of make that connection. Degrees, think 180. When I say radians, I want you to think of pi. Okay, so radians, think pi. Degrees, think 180. If you remember those 2 things, then all of that becomes automatic. Okay, we don't even have to memorize it. All right, so let's look at a few of these. I think we only got through like maybe 1 or 2 of each, but I had some extras that I wanted to just take a look at. And that's because converting between degrees and radians is a really important trick. So it's not something I really want to skip over quickly. All right. So in this one, we're trying to get rid of the degrees. Think of 30 degrees as a fraction like that. Where is the degrees in that fraction on the left? It's in the top. We're trying to convert to radians. So where is the degrees going to go? It's going to go in the bottom, which means radians is in the top. Now, when you write down radians, we never label it RAD. Okay, we don't label. The only time you put a label on an angle is if you want it in degrees. That's the only label you'll ever see on an angle. So degrees is in the bottom, radians is in the top. What's the number that I said to always connect with degrees? What? 180. So 180 degrees. And in the top is radians. What's the number that I said to think of when you think radians?
Pi.
Pi. Now, generally, when you convert between degrees and radians, you leave the answer exact. All you do is reduce it as much as you can.
Pi
what-
over 6.
Yeah, this 30 goes into itself once, and 30 goes into 186 times. So that is pi divided by 6. So now, once you start to know some of the basic ones, like 60 degrees, you should be able to do pretty quickly based on knowing 30 degrees. How much would 60 degrees be? Yeah.
Pi over 3 radians.
Right, you would double that. Okay, so that's what starts to get helpful when you learn some of the basic ones. You can do the other ones faster. All right. Let's try this one. I'm not sure we did this one in class. I don't remember. 45 degrees. Okay, converting to radians. Where would degrees have to go to cancel out? If you put degrees in the top, you're going to have degrees times degrees, which would be degrees squared. Yeah. Yep, it's going to go in the bottom. That means radians is in the top. And the number that we always put with degrees when we're converting, yep, 180. And the other number we always use is the pi. Okay, so we've got 45 times pi over 180, and we're just going to reduce as much as we can. All right, what number goes into both 45 and 180?
I think it's 45.
Yeah, 45 is the biggest. 45 goes into itself once. How many times does 45 go into 180? James?
4.
4 times. So we get an answer of pi divided by 4. So that's how you convert degrees to radians, leaving it exact. I think I have one where I asked to round. Yeah, let's do this one. So find the radian measure of the angle, and this time they say to convert to 2 decimal places. Okay. What are we going to multiply by to change that from degrees into radians? Yeah,
Pi.
pi. And we're going to divide by
180.
180. Perfect. Now, can you reduce? Yes. But since you're rounding to 2 decimal places, it doesn't matter. I guess if you want to save yourself a little typing on the calculator, just divide by 10 real quick. So 50 pi divided by 18. But again, reducing it doesn't matter because you're rounding it. Calculator.
8.73.
Okay. So one thing you want to be careful when you type that in, make sure you use the pi button. So 50, and then second, and then the exponent sign.
8.73.
So yeah, we're going to get
We
0.873.
divide by 50 by 180 instead of by 18.
Oh, did I do? Oh, thanks. Yeah. Yep, so 8.73. And no label. No label at all. Okay, it's always understood when you write an angular measurement in trig, if there's no label, it's radians. Okay. All right, any question on that one? Now, let's take a look at a few converting the other way. Converting 2 degrees. Okay, this time pi is in the top. Pretend like it says RAD next to pi. Where would the RAD have to go to cancel out? Yeah.
On the bottom.
It's going to go on the bottom because we're trying to convert 2 degrees. So radians goes on the bottom. What's the number that we always connect with radians when we're converting? Yeah.
180. No, wait, pi.
Pi. Yep. Pi on the bottom. Degrees is going to be on the top. And what's the number that we're going to connect with degrees?
180.
Yep, 180. So radians cancels out, but that's invisible. The pi cancels out, and we can reduce. How many times does 2 go into 180?
2 or 90.
90. So 2 goes into itself once. 2 goes into 180 90 times. And what am I left with when I convert that to degrees? Yep.
270 degrees.
Yep. 3 times 90 degrees. Do I need to put the label on it?
Yes.
Yes, I do. Because it is a degree. If you don't put the label, it is radians. And you will lose some credit if you forget that label. In order to type the degree symbol on the test, it'll come up in the box for you, and you'll be able to click it. Okay, any question on that? All right, I have one more we can convert and then round, and then we'll look at the new stuff. Again, let's get used to not seeing radians there. Okay, what do I multiply by to change 3 radians into degrees? Right?
180.
Let's see, so 3, yep, multiply by 180 and divide by pi. Perfect. This is one that you will notice a difference if you don't use the pi button. Okay, your answer will be off. Okay. If you use the pi button, 3 times 180 divided by pi, that's the most accurate way, and you get 171.89. If you use 3.14, okay, that's going to be 3 times 180 divided by 3.14. Okay, you get 171.97. If we're rounding to 2 or 3 decimal places, there's a pretty big difference between 0.88 and 0.97. They're not the same. Okay, so always use the pi button when you're doing a conversion. Okay. Any questions on that? All right, so now we're going to take a look at the second part of 6.1, which is on arc length and angular velocity. I'm going to start with arc length. So arc length is when you are measuring part of a circumference on a circle. That's an arc. So arcs are part of circles. And the first thing to understand is that the size of an angle that creates the arc and the length of the arc are what we call directly proportional. What does that mean if 2 different things are directly proportional? Yeah?
The ratio of them will always be equal to will always be constant.
The ratio of them will always be...
Will always yield a constant. So A divided by B equals C, in which A is a number.
Let me think about that one a little bit more and see, possibly. I'm thinking of something a little different here in terms of how if one thing changes, how the other thing changes. Yep.
When one goes up, the other goes up. When one
Right.
goes down, the other goes down.
Right. Directly proportional means, yeah, exactly. They change in the same way. So,
They stay constant. When one goes up, the other goes up. When one goes down, the other goes down.
so if we look at that, how much of an angle? Well, now, how much is that angle?
90 degrees.
That's 90 degrees. And how much of the circle does the arc created by that angle take up? Takes up a quarter. Okay. So a 90-degree angle creates an arc that takes up a quarter of the circle. All right. So now, let's draw that angle. Now we have this arc. If arc size and angle size are directly proportional, like I said, then if you say double one, the other one should double. So before we check it out, let's just look at this one. If you double 90, how much do you get?
Half the circle.
So if you double 90 degrees, you get
180.
180 degrees. And if you double a quarter of a circle, how much do you get?
Half.
A half. So let's see if that works. Okay. This angle that I drew right here in black, that's a 100-degree angle, or 180 degree. And how much of the circle is 180 degrees?
Half.
It's half. Yeah. So angle size and arc size are directly proportional. If you triple the size of the angle, you will triple the size of the arc. If you make the angle 1/3 as big, you will make the arc 1/3 as big. They are directly connected. And when you look at the word directly proportional, what other word do you notice in there that has something to do with setting up an equation? Yep. Yep.
Proportion.
Proportion, yes. When two things are directly proportional, you can set up a proportion to calculate one or the other. Right? So a proportion means we're going to be able to set up something like that. If they were not directly proportional, then we couldn't do that. Yep. Nick, can you just wait for one person and come back?
Yeah.
I think there's two people out there. Thank you. All right, so let's look at this picture. This is a picture that's showing two arcs and two angles in the same picture. I've labeled each angle using the Greek letter theta. They are different angles, so I need to label them a little differently. One's theta 1, one's just theta. And then I've also labeled the arcs that correspond to those angles. Arc S goes with angle theta. S1 goes with theta 1. And if they are directly proportional, then we can set up a proportion with those four things. There's lots of ways we can set this proportion up. We just have to make sure, however we set it up on the left, we have to set it up the same way on the right. Can somebody give me two things that I could plug into my proportion? And let's start with the left-hand side. Anyone have an idea of what two things we could fill in on the left? Yeah?
Theta over theta 1.
Sure. We could do theta over theta 1. Now you have to set the right side up using the same pattern. What would go on top on the right side now? Yeah? S. And on the bottom? S1. No matter how you set it up, it would come out the same, as long as you compare the left and the right correspondingly. Yeah.
In the video, you set it up as theta divided by s equals theta divided by s1.
Yeah.
Is that the same?
Because when you solve a proportion, does anybody remember the technique you use to solve a proportion? Yeah. You cross multiply. So when you end up cross multiplying what you just said and what I have, the cross products come out the same. Yeah. Okay, now you can't solve a proportion if there's four variables in it. You gotta have some numbers in there. So when you're setting up a proportion, generally you need to start on one side with something you already know. So let's say that I wanted to convert some amount of feet to some amount of inches. Well, I can't, let's say I said to you 5 feet. Well, I can't solve that unless I know something else. I have to start with a fact that's true on one side. Doesn't matter what fact. It can be anything that's true that connects feet to inches. Anything. So can somebody give me a fact that connects feet with inches? Any true fact? Yeah.
1 foot is 12 inches?
Sure. You could do 1 foot is 12 inches. You could do 10 feet is 120 inches. Generally, we try to keep it simple. But yeah, start with a fact that you know on one side. They give you a piece of information they want you to work with, and then you can solve for the piece of information you don't know. Okay, but that is the key. Okay, starting with something that you know. We need to do the same thing here. We have to start with something we already know. So I'm going to give you a hint, and then I want you to see if you can tell me the other part of the hint. Let's suppose that theta 1 is 1 radian. Now, I could suppose something else. That's the easiest thing for me to use. Just like here, I could suppose that you're working with 2 feet instead of 1 foot. I could still give you a conversion. 2 is to 24. Okay? But 1 is generally an easier number to work with. So let's suppose that theta 1 is 1 radian. If this angle is 1 radian, then we automatically know something about S1. And it's what we reviewed just a few minutes ago. If this angle is 1 radian, it automatically makes this arc a certain size. Does anybody remember how big this arc is if that angle is 1 radian? Yep.
Makes it 2 times as large, I believe.
We don't know any specific number. All we know is its relationship to something else in the picture.
Then 2 times the value of theta 1.
So again, we don't know any numerical value.
Oh.
We just know that if this is 1 radian, this arc is automatically a certain size.
2 radians then.
No, again, we don't know a number. We don't know anything numeric about S1, but we know something about it.
The radius of the circle?
It would be the same as the radius of the circle. Okay. Yes. Why? Well, it's like saying why are there 12 inches in 1 foot? It's a fact that's a definition that's been created. Well, this is more like a mathematical definition. If the angle is 1 radian, then the arc is automatically the same size as the radius. So using that true fact, we can fill in some of our proportion and then cross multiply and see what we get. Okay, so let's fill in what we can. Theta, we don't know. That's going to be something that's given to us in the problem. Theta 1, we're going to let equal 1. Now, in the feet and inches problem, I plugged the true fact in all on one side. The way we're doing it, we're going to be plugging the true fact in on the bottom. That's fine, okay? The true fact, it has to be somewhere in the proportion. Whether it's all on one side, all in the bottom, all in the top, it's got to be somewhere. Okay, so we fill that in. S we don't know. Okay, that would be given to us in the problem. But if this angle is 1 radian, we automatically know that S1 would be equal to the radius, which would be something given to us. Okay. And now let's cross multiply. If you cross multiply, what's S times 1 give you? Yeah? S. And what do you get when you multiply the other diagonal? Yeah.
Theta times r.
Yeah, theta times r times theta, same thing. You get that formula. You get S equals r theta. And that is the formula for finding the length of an arc in a circle. You need to know two things. How big the circle is, what's the radius of the circle, and how big of an angle did you make in the circle. So the S stands for arc length, R stands for radius, and theta is your angle, but this is where it becomes tied in with what we did in the last part of the section. The angle has to be in radians. So if they give you an arc length formula and the information they give you is in degrees, before you even start plugging in, change your angle to radians. So the way the formula works is generally they'll give you 2 out of 3 pieces of information, and you're going to solve for the third one. Okay. So let's see if we can find the length of an arc in a circle that has a radius of 2 inches, and the angle that we're going to be drawing in the circle is pi over 4. And they don't need to give you a picture with that. That's enough information. Okay. But I gave you guys a picture so you can see what's going on. Okay, so find the length of that arc in red. That's what they want. Amanda, if you want to go ahead. Well, since it says find the length of the arc, the first thing we're going to need is the formula. Can someone remind me, what is the formula for arc? S equals r theta. Determine which 2 things they give you and fill those 2 things in. Okay, well, the question says find the length of the arc, so that means we're solving for which letter? Yeah, no. Yeah, solving for S. Okay, what's my radius that they give me? Right? 2. And what's my angle that they give me? Nick.
Pi over 4.
Pi over 4 what?
Radians.
Radians. How do you know that?
Because there's no degree symbol.
Because there's no degree symbol. Exactly. Because it's in radians, I don't need to do anything with it. That's exactly what it needs to be. Okay, so let's multiply that together. When you multiply 2 pi over 4, when you multiply 2 pi over 4, what do you get? When you multiply that and reduce it as much as you can. Yeah, go ahead, Bill.
Pi over 2.
Yeah, so you're going to get 2 pi over 4, which reduces to pi over 2, and that needs a label. Okay, what did we just solve for in this word problem? Yeah,
The arc length.
the arc length. So yeah, what would the label be?
Inches.
Inches. Yep. So the length of that arc is pi divided by 2, or about 1.57 inches. Okay, that's it. That's how you find the length of that. Any question on that? All right, so let's try this one, which is a little different. It says find the radius of the circle if the arc length is 3 pi 8 and the angle is 60 degrees. Okay, so first up, we need our formula. Joe, what's the formula that I'm going to use to solve this one? Yeah, perfect. S equals r theta. And can somebody else tell me which letter I'm going to be solving for this time? How about Cole? What letter am I solving for? Nope. Solving for S. What is, if you read the question, what
you find R?
finding r. It says find the radius. Okay, so that means we must already have the s and the theta. Cami, what's the s in this case? So it says the arc length is 3 pi. So we're going to fill that in. We just said we don't know the r. And what's theta in this case? Yep. 60 degrees. That's the angle that they give me. Can I fill that in? Wait, no, what's wrong with that?
It's in degrees and not radians.
Right, it's in degrees and not radians. So off to the side, let's fix that. Do you remember, Moises, what do we multiply by to change that to radians?
Times pi divided by 180.
Yep. And when we reduce it as much as we can anybody tell me what 60 degrees is going to become? Yep, pi over 3. Okay, now let's solve for r. Okay. How would we get pi over 3 on the left side? Yep.
Divide by pi.
Okay, you're going to divide by pi, and can we get the 3 over there at the same time?
Yeah, but divided by 3 pi. Or wait.
So dividing
or
by
pi over 3.
Okay, so is there another way to say dividing each side by pi over 3?
Multiplying by 3 over pi?
Yes. So it's a little easier to think of this one as multiplying each side by 3 over pi. So the 3's cancel, the pi's cancel. That's on the right. And then what am I going to get on the left for my final answer when I do that out? Yeah.
9
9.
radians? Or
Well, think about what did we solve
feet.
for?
Feet.
Yes, we solved for the radius. Okay, the radius is a linear length measurement. And in this problem, the length measurement was in feet. So that's an example where they give you the s and the theta and you solve for the r. The first one I gave you the r and the theta and you solve for s. But that's the idea of the arc length formula. Questions on that? All right, so the last thing. Okay, angular velocity. So think about what an angle measures, right? An angle can measure movement on a circle. It's how we describe an amount of rotation. How fast something is moving, that's generally, we can describe that with velocity. So what angular velocity is used to describe is something moving on a circular path. Okay, it's like something spinning. That's what angular velocity is used for. So angular velocity, angular speed, just synonyms, same idea. But the more important question is, why do we need that? Why do we need angular speed? We already have a way to measure speed in a linear sense, right? Miles per hour or feet per second. Why do we need to measure something in like radians per second? Why would something spinning need a different way to describe how fast it's going? Yeah?
Because it could be in one place, but it could be spinning really, really fast. Or if you're doing orbital mechanics, you'll definitely need radians because it's extremely hard to convert from regular velocity to angular velocity.
Well, hopefully I can make that a little easier. Hopefully it won't be too hard to do. But that's what I'm going to try to explain looking at this disk in a second, why we need angular speed. Yep.
Could RPMs be another way of describing it, or
Yep, that's measuring angular speed using revolutions, specifically revolutions in minutes. Yep. So if you look at those three dots, okay, we've got the black one in the center, the red one, and then the black one that's towards the outer edge. Okay, if I take that circle and I go like this one time, each dot just made how many revolutions? Yeah, one. Each dot made one revolution. It each had its own revolution, but they each made one revolution. They all had that in common. Now, different question. Which dot traveled the farthest? Even though they all made one revolution, which one traveled the farthest? Yeah?
The outer black one.
Right, the outer black one traveled the farthest. Right? If you watch it as it moves, and you were to draw the path that it's following, it went the farthest. Okay, so keep that in mind. The outer black one went the farthest, the red one went second farthest, and the one right in the center traveled the least amount. What's the formula that we use to find a connection between distance, time, and speed? It's a formula that has those 3 letters in it. Remember, I think we've talked about the formula. Yeah, I know we've talked about it when we talked about like a train problem, the train, and Sue was taking the train or something. We did that formula back then. Anybody remember formula? Yeah.
speed is equal to the change in distance over time?
So go ahead, give me the 3 letters. What equals what?
S equals d over t.
Okay, how about if you solve it for distance? What would it be?
Solve for distance.
Yeah.
S times t equals d.
Okay, so distance equals rate times time. I'm just going to use R for rate. I'm going to stay away from S because we're using S for arc length today. So it might be confusing if I use S for distance here, but in physics, a lot of times they do. So I'm just going to say distance equals rate times time. So everyone agrees that all those dots made exactly 1 revolution. But the outer black one traveled the farthest. Now, if you compare the time it took the middle black one, the red one, and the outer black one to all do 1 revolution, how do the times compare? The time it took for this one to make 1 revolution, the red one to make a revolution, and the outer black one. If you measure those 3 times, how would they compare?
They all went the same.
Right, all the times are the same. Now, if all the times are the same, but this one traveled the farthest, what does that mean based on that formula? All the times are the same, but the one that I'm pointing to traveled the farthest. Yep.
That one went faster.
Right, that would mean that that one is going faster. In fact, it would mean that every single dot from the center to the edge is traveling at a different speed. Right? Because they're all making a revolution in the same amount of time, but they're all traveling a different amount. That's going to be a very confusing way to describe angular velocity, because then the speed of that disk would depend on where the dot is that you're measuring. So we don't want to describe angular speed using distance equals rate times time, right? At least not thinking of it the way we just did. What we want to do is, instead of describing the distance as an amount of travel that it does, we're going to describe it as a rotation. And then every dot on this disk has exactly the same speed. All right? Yes, the rotation size is different, but the rotation itself it's still, like if we go like that, maybe they're making 1 rotation in 3 seconds. So maybe it takes 3 seconds to do a rotation. And that's the same for every single dot. And that's what we want, something the same. Okay? So that's why we use angular speed. If they don't give you any direction in a problem, we always assume that angular speed is radians per time unit. Okay, somebody else mentioned, could you use revolutions? If they say you can, yes. But if they say convert the following, and they want an answer in angular speed, the default answer is always radians, unless the directions say otherwise. The default on the time unit, there isn't one. Time can be whatever time they give you, minutes, seconds, hours, days. Now, if you compare that to linear speed, the only difference in linear speed is how are you measuring the distance. In linear speed, you're not measuring distance as an amount of a revolution. You're measuring distance using feet, inches, miles, centimeters, kilometers, something like that. Okay, so angular speed and linear speed, very similar idea. The only difference is how are you measuring distance? Are you measuring it in a straight line, or are you going to measure it as something revolving? Okay. And you can convert between the two, and that's what we're going to do. Now, the easiest way to deal with all the conversions here is basically to use what's called dimensional analysis. It's exactly the same way I tried to show you to convert between degrees and radians. If you have a unit in the top and you don't want that unit anymore, you want to get rid of that unit, then you need to put it in the bottom in the next fraction. Right. So if you don't want to use dimensional analysis, you can come up with like all kinds of formulas to try to do it. It just becomes very cumbersome that way. And it's like you're memorizing little tricks for every type of problem you come across. There's too many different kinds of problems I'm going to give you. So dimensional analysis, that'll cover how to do everything. Right? And what we're going to do is we're going to start with a dimensional analysis problem, not even converting between angular and linear. We're just going to convert like seconds to years, okay, a conversion like that. And that's an easier thing to start out with. Well, days to months. Okay, so let's start out with 3 days. Each time you convert, you're going to multiply by a fraction. I would expect that you know most basic conversions. What I consider basic conversions, how many seconds in a minute, minutes in an hour, hours in a day, days in a regular year, how many inches in a foot, how many feet in a mile, feet in a yard. That's pretty standard. I wouldn't expect you to know something like how many centimeters in a mile. That's not something most people know off the top of their head. All right? But the conversions I just mentioned, you would need to know those. As you convert, you go one step at a time. We're trying to get from days to minutes. Is there a unit that we can go to in between days and minutes?
Hours.
Yes, we're going to go to hours. So the first thing we're going to do is we're going to get days down to hours. Think of 3 days like that. It's a fraction. I want days to be gone. Where would days go in the next fraction?
Bottom.
It would go in the bottom. And the unit that we're trying to convert to get us eventually to minutes, but this is one that's kind of in the middle, is hours. So once you set that up, now you need to fill in the conversion. We can come back and fill it in. That's the easy part. It's more important we get all the units in the right spot. Once we get that done, we want to go from hours down to minutes. So now we want to get rid of hours. Where's hours going to go in the last fraction? Yep, at the bottom. And we're going to put minutes in the top. Now let's fill in the conversion. I need a fact that connects hours and days. It can be any fact you want. Preferably the simplest fact would be nice. Can somebody give me something true that connects hours and days? Yep.
72 hours is 3 days.
How many hours is 3 days?
72.
Okay, so you could put 72 hours is 3 days. Can somebody put even a simpler conversion? That one would work fine though. Yep,
24 hours in 1 day.
sure. A lot of times when we write a conversion, it usually has a 1 in it. Like if I asked you convert feet to inches, you'd probably tell me 12 inches is a foot. You could say 4 feet is 48 inches, but you'd probably use 12 to 1. All right, so there's our first conversion. Now I need another conversion. What is a fact that's true between hours and minutes? Yep.
60 minutes and 1 hour.
Yep. 60 minutes and 1 hour. Hours is gone. Days is gone. And now you multiply straight across. In this case, we did end up with all ones in the denominator. That doesn't always happen. So we've got 3 times 24 times 60. So it's 4,320 minutes. If the dimensional analysis made sense there, then it's not going to be any harder when we start doing angular velocity. Same concept. Okay, any question on that one? Okay, 50, actually, can somebody read that to me? How do you read that? 50 what? Yeah? Right, that's 50. A lot of times you read the division line as per. That means you're going to be traveling 50 feet in 1 second. So the last problem was converting a time. This is converting a rate. A rate has 2 components to it. Time is one of them, but the other one is distance. So we have to get each part of the rate in the right unit. Let's start with the seconds. We want to get seconds eventually into what unit?
Hours.
Hours. What unit can we go through in between getting seconds to hours?
Minutes.
Minutes. So we need a conversion between seconds and minutes. We'll come back and fill that in. And then I need a conversion that's going to convert minutes to
Hours.
hours. Where would minutes go in the next conversion? Top. And that means hours would go
Bottom.
bottom. So now if we just look at our units, that's gone, that's gone. If we filled that in and did it out, what would my speed be measured in now? Yeah,
Feet per hour.
that would be feet per hour. So we've got the time unit right. We got hours. Now I need the distance unit. I'm trying to convert feet into what?
Miles.
Miles. Even if you don't know how many feet in a mile yet, we should still be able to get the units in the right spot. Where is feet going to go?
Bottom.
Top or bottom? Bottom. And in the top?
Miles.
Miles. So now if you did all that out, you have miles in the top, hours in the bottom. Now let's fill in all the conversions. Connection between seconds and minutes,
60 over 1.
60 over 1. Connection between minutes and hours,
60 over 1.
60 minutes and an hour. And connection between miles and feet.
5,280.
Where does that one
mile,
go?
2,500, or 5,280 feet.
5,280 in the bottom, 1 in the top. So this time you can see we did not end up with all ones in the bottom. Okay, so let's do that out. 50 times 60 times 60. So that's the top. And you're going to divide by 1 times 1 times 1 times 5,280. So that's 34.09. And what's my unit on it? Miles per hour. Yep. Okay. Any question on that one? Okay. So I think this is the last one. So the first one was just converting a time. The second one was converting a rate, which has a distance and a time. And the third one is going to be converting a rate again, but we're not only going to be converting a time unit and a distance unit, we're going to be converting a distance between angular and linear. Okay. So let's try 200 radians in 1 second. That's the speed that this is spinning at. Now, just to kind of give you an idea of what's happening, when you convert angular to linear, imagine a wheel, like spinning. If you had a rod, put the wheel on it, you spin it. So now the wheel is spinning on the rod. So now you take that rod and you dump it so the wheel falls off. What's going to happen is instantly when that wheel hits the ground, assuming it doesn't fall over, it was spinning, but now it hits the ground, all of a sudden it's going to take off in a straight line. That's basically what you're doing when you convert angular to linear. It's like if something is spinning and all of a sudden all that spinning energy converted into moving, like horizontally, how fast would it be rolling on the ground in front of you? That's what you're figuring out. So actually this one we are not converting to linear yet. That's going to be the next one. This one is just angular to angular. All right. How do I convert seconds to minutes? How about James? How do we convert seconds to minutes?
60 seconds in a minute.
Yep, perfect. 60 seconds in 1 minute. Okay, so we got the time unit, radians per minute. Now I want to convert radians to revolutions. Where is radians going to go if I'm trying to convert to revolutions? Yep, it's going to go in the bottom, and revolutions is in the top. What's the connection between radians and revolutions? Yeah.
1 revolution is 2 radians.
1 revolution, yeah, I like that, is
2 pi, right?
2 pi. Yeah. Okay, so radians is gone. And now we multiply that out, and we would have a speed in revolutions per minute. Okay, I'm going to say multiplying it out for you, because I want to do the last one. All right, so now, we're going to look at the example where we have a wheel that's spinning, and then we're going to convert that into linear. I'm not going to do part A. Part A is converting from revolutions per minute. If you see the if you see the abbreviation RPM, that stands for revolutions per minute. Okay. Part A is converting between RPMs and radians per second. It's exactly what we just did right here. RPMs and radians per second. It's the other way, but it's still what we did in 7C. So let's just do part B. So it says find the linear speed in feet per second. All right. Well, what are they giving me to start with?
A wheel with a radius, so it gives us the radius of 18 inches,
Yep.
and the speed it's rotating at, which is 100 Or 1,850
1,850,
rotations.
yeah, rotations or revolutions in a minute. Okay, let's straighten out the time unit first. What's the conversion that I'm going to multiply by to fix that so it's in the time they want?
1 minute is 60 seconds, made on 5 seconds.
1 minute, 60 seconds. Okay, so that's the time. Now we have to convert revolutions to feet. How many feet in a revolution? Yeah,
Isn't it like dependent on the radius?
right. There is no standard conversion. How many feet in a revolution? How big of a revolution are you making? Is it a small revolution, or is it a revolution around like a huge circle? So the conversion from angular to linear is different in every problem. So we have a wheel that has a radius of 18 inches. I'm trying to get a conversion to get rid of revolutions. So I want revolutions in the bottom, and I want feet in the top. If I trace this out, right, I'm drawing one revolution right now. If I put a piece of string on that, what would I be measuring about that circle? Yeah,
The circumference.
I'm measuring the circumference. The circumference is a revolution. Right? So if we can figure out what the circumference of that circle is, that will tell us exactly how big or how many inches in the circumference. We really need feet. So we should probably change 18 inches to feet before we even start. What's 18 inches in feet?
1.5.
It's 1.5, yeah. Let's just put that down. So the radius of the circle is 1.5 feet. What's the formula for circumference?
2 pi r.
2 pi r. So what is the circumference of this circle as an exact answer? Yep,
Circumference equals 3 pi.
3 pi.
Feet.
Feet. That's how many feet are in one circumference or one revolution in this problem. That is not a conversion you can use in any other problem unless they give you a circle with a radius of 18 inches again. Okay. So there are 3 pi feet in one revolution. Okay, so that is a conversion you can't memorize. You have to memorize the formula for circumference and then use that. Okay, so now if we do that out, we will have feet in the top, seconds in the bottom. I would normally tell you what you could round to. I didn't in this one. I just say round to 2 decimal places. So 1850 times 3. Just like when we're doing conversions that we need pi, use the pi button. And order of operations will handle all that fine. Okay, you can type that all in. You don't need any parentheses the way I did it. And you get a speed of 290.6 feet per second. Let's put that up here. Okay, so that's pretty fast. If you imagine a football field is 100 yards, right? So that's 300 feet. So it's doing almost the length of a football field in a second. It's pretty fast. All right, any question on it? All right, so that's the 2 things for today, arc length and angular velocity. Tomorrow and Wednesday, we will do 6-2. Get the homework. Okay, so homework is just the first part, page 324. 56 to 61 and 70 through 73. In the video from last year, it is combined with another section, but we didn't do it today. I just wanted to do this one.